Okay, so welcome everybody. Welcome to the Colloquium. And today it is our pleasure to welcome Andrew Taylor. And many of you already know him because he did have postdoc here and he did his PhD in Oxford, postdoc here, then Geneva. And now he's working at the Dublin Advanced Institute for Studies. Advanced Study Institute, sorry. Like the Princeton one, but apparently it's younger and very vibrant, and he's going to tell us about probing extragalactic magnetic fields with different data sets.
Yeah. You got it?
See?
Okay, cool, thanks. All right, so first off, it's really a pleasure to be here. I was a postdoc here like 6 years ago now. It seems like a long time ago. And it's great to be back. Great faces, a great city to be back in. Okay, so talk about extragalactic magnetic fields. I wanted to give you a picture, fix a picture in your head to be relevant throughout the talk. Situation is that this is the results from an n-body simulation, and the purple particles are dark matter particles, and the yellow particles are where the wells got deep enough that the baryons started galaxies, and as AGN associated with the yellow blobs. Okay, so that's and this is a cluster region. It's 100 megaparsecs because the universe is this is a homogeneous scale. The universe will repeat itself on these larger scales, or not repeat itself, but it's homogeneous on these larger scales. Sorry. So this is the simulation in box size, and the simulation was started from these conditions for the matter distribution with these very mild density fluctuations in them. Okay, and the reason I'm talking about this, which seems a bit different to the title, is that the question is these extragalactic magnetic fields. When did they come from, and when did they come from? This simulation was started, let's say, at a redshift of 20. And the question is, are there extragalactic magnetic field seeds present back then, or were they formed later on when the structure evolved and collapsed, and these galaxies and AGN formed, and then those perhaps feedback back out into the voids to see the extragalactic magnetic fields? So that's one of the questions that I won't give an answer to, but it needs to be addressed, along with the strength, of course, of the extragalactic magnetic fields. And it's actually the strength of the extragalactic magnetic fields I'm focusing on. Okay, so I want to highlight to you the uncertainty that's present in the extragalactic magnetic fields, how embarrassingly uncertain the strength of them is. I want to talk about possible lines of attack of ways that we can probe this extragalactic magnetic field. I want to talk about two methods, using cosmic rays and using pair cascades. Of course, so the underlying principle is you've got these extragalactic magnetic fields, and you want to throw charged particles into those regions, because of course the charged particles couple to the fields, and they'll be your probes of these regions. And ultra-energy cosmic rays are one candidate for doing this, and I'll explain why high-energy photons can also do that later on. Okay, I want to talk about recent developments in observations. So it's not just theoretical work. There's been great progress from observational astrophysics that complements this work. And finally, I'll talk about the consequences. We'll come back to on this uncertainty. So first off, what did we know, or what have we known for a while, using just radio data? Of course, radio photons, they also probe magnetic fields through the rotation measure. So we have our distant AGN, much more than 100 megaparsecs actually, but so we're going to put it out, let's say, at a gigaparsec. This is a distant quasar in reality, and they look at the rotation measure from this distant quasar. In fact, of course, you don't know what the original rotation measure is, or the plane of polarization is of this distant blazar, or quasar, sorry. But you can measure the change in the rotation, polarization rotation of it as a function of different wavelengths, and you measure this differential quantity. And it is one of the strongest probes of extragalactic magnetic fields that we've had at least until recently. Okay? In terms of how strong a probe this is, I wanted to draw your attention to this. So this is the Faraday rotation method that I'm talking about, and we're getting of the order of nanogauss fields with coherence lengths of 1 megaparsec, and that's what we're able to probe using the rotation measure method. Okay, so using radio data, that's where we can get at the moment. So we got to the nanogauss level, and what could we do for the future? How much better than this? Well, the SKA is the hope, and it can go down to the 0.1 nanogauss level. And just to remind you that the SKA is not really near future. It's still got it will happen. It's going to be a long time. So progress is slow. Okay, so I wanted to talk about why high-energy astrophysics can say quite a bit about to help us understand this plot here. Also, let me explain a little bit more about this plot. Here we've got, this is the astronomical unit length scale here, so that ohmic diffusion will kill small scales fields in the Hubble time, so we wouldn't be able to sustain these fields for very long if they were too small, and this is the Hubble scale up here. And then, of course, we've got some other methods when the fields become very strong that we'd use for like probing galactic magnetic fields. But essentially, it's the rotation measure that's the best method for these extragalactic magnetic fields. Okay, so firstly, I want to talk about cosmic rays and why they offer themselves as an actual probe. So talk about ultra-high-energy cosmic rays. These are 10 to the 20 eV cosmic rays. I've put us in this yellow patch here. I've put my source here, which is some, I say 50 megaparsecs away or so. It's a nearby ultra-high-energy cosmic ray source. And the reason why it's a very good probe is, of course, it's a charged particle, so it couples to the field. But also, its interaction cross-section is of the order of, it's of the order of 80 millibarn or so. And the number density of the photons it interacts with are primarily the infrared backgrounds, and they have a number density of the order of 1 per centimeter cubed. So if you put those two numbers together, you get interaction lengths of the order of 30 megaparsecs. So such that ultra-high-energy cosmic rays can propagate to us, but only from local regions. Okay, so well, one hope using ultra-high-energy cosmic rays is using the deflection of the cosmic rays as arriving from a distant, or from a nearby distant source. So here's our source here. I've put it at some 100 or, I don't know, 70 megaparsecs away from us. And the cosmic rays got to propagate through magnetic patches. And we'll have these magnetic patches of the coherence lengths of 1 megaparsec. And the magnetic fields in each magnetic patch is going to be randomly aligned with neighboring patches, such that it's going to, in its propagation, the angles are going to incoherently add, and we're going to get a random walking angle of the cosmic rays as they're propagating from the source to Earth. So in this sense, we can look at what sort of angular broadening you might expect of a cosmic ray arriving from this source. Okay, so in terms of the Lama radius, if I put in a 0.1 nanogauss field strength, okay, and 10 to 20 eV cosmic ray, we've got a Lama radius of a gigaparsec. I put in a coherence length of a megaparsec, so each patch I can deflect something like 10 to minus 3 radians. And I'm going to go through some 100 patches to get to Earth, so it's going to be something like 10 to minus 2 radian deflections, which is half a degree. Or if the cosmic rays aren't protons, it's going to be something quite a bit bigger, let's say 13 degrees for iron nuclei. Okay, so we can look for this deflection, and this has been done by, in fact, I was talking about rotation measurements before, and one of the key people in this field for that has been Phil Kronberg. And it's actually interesting because he's also branched out, he's actually looking at other methods too of measuring extragalactic magnetic fields. So this is actually a Phil Kronberg paper here recently, and he's looked at the distribution of ultra-energy cosmic rays. These are cosmic rays with energies above, say, 55 EeV, and This is measured by the Auger instruments in Argentina. The blue line, this is an LB plot, and the blue line is the region where it's got actual exposure within that region. But that you can see that there does seem to be a clustering of events around the direction of Sen A. Okay, so Phil Kronberg, in his paper, motivated this as to be a signature of the extragalactic magnetic field strength in the direction of Sen A. And so here we've got the clustering. We've got some 13 cosmic ray events where isotropy would give us about 3. So it does stick out. It's actually the strongest correlation signal that seems to be in the data at the moment. And in terms of field strengths, that if the cosmic rays are protons, that is, the field strength that you get in these regions that you'd need in that direction of the order of, they're strong, they're 20 nanogauss. But then it could be that Sen A, of course, is a local object, so that you've not really gone into the proper void region, so you're not probing real extragalactic magnetic fields. Anyway, this is suggesting itself as a probe, and that's the point I wanted to get across. Okay, that said, you have to be careful. That is a probe that has caveats, and the main caveat is the composition. Okay, so the evidence is that ultra-energy cosmic rays seem to be getting heavier as the, I'll show that in a following slide. The cosmic rays seem to be getting heavier at the highest energies. So a proton-type composition does not seem so well motivated, whereas, so I wanted to address that this is work I've done with Roy Liu in the audience here and some other collaborators. We're looking at the deflection of cosmic rays actually in the galactic magnetic field. And of course, in the diagram I showed you a few slides back, and I looked at the deflection of particles essentially coming from Sen A and random walking, there's of course a local distortion effect from the galactic magnetic field on top of everything. Of course, for protons, it can be subdominant, but actually for nuclei, even the galactic deflections can be significant. So just to show you that this is the same circle here, and these you can get for oxygen-type compositions, you can get large deflections in just the galactic magnetic fields. So of course that puts a dampener on things. It limits this method somewhat. But there is hope that we'll understand the galactic magnetic field. There's been some progress, and there will, of course, be, I mentioned the SKA, there will certainly be progress in understanding the galactic magnetic field in the near future. And then it'll be the case of undoing, or being able to undo the damage done by the galactic magnetic field to probe the extragalactic magnetic field in the more distant future with this sort of method. Okay, so I wanted to get across that the cosmic ray composition doesn't look like it's light at the highest energies. Again, this is Auger data. I keep referring to Auger data because the Pierre Auger cosmic ray detector is the biggest in the world, and it's got the best statistics. So here we've got the flux measurements, but I really want to focus your eye on these measurements here. So when an ultra-energy cosmic ray arrives to Earth from across the universe, it dumps its energy in the atmosphere to make a cascade. And the number of particles in the cascade keeps growing, and the energy per particle keeps decreasing until the center of mass energy that the particles can make in the collisions is not sufficient to generate more particles. And then the cascade starts to die again. So the cascade has a natural profile, and the distance from the top of the beginning of the shower to the point where the number of particles in the shower is maximum. That distance is referred to as Xmax. And this has been measured by Auger. It's not just Xmax, the mean of it, but the second moments as well, the RMS of the Xmax, have both been measured. And what's exciting about this result is that a consistent picture is emerging from this. It looks like the composition is starting at, say, a few times 10 to the 18 eV, is turning over and is becoming heavier. And so the heavy-ish nitrogen type compositions, as I mentioned before, seem motivated at the at the highest energies that they can probe using the X-max data. Okay, so the cosmic ray composition looks like it's getting heavier, and like I said, that makes life difficult for using cosmic rays as a probe of the extragalactic magnetic field. But we can, if we persevere, we can go a little bit further. Okay, so I quickly wanted to address how you go further. We want to work out how cosmic rays transmutate as they propagate. So they're going to disintegrate. That's the dominant process is through photodisintegration, where the nucleus interacts with a high-energy photon and emits a nucleon and becomes a bit lighter. Okay, so here's the cross-section for that here. So for example, I want to fix on an example. So do it for iron nuclei. So we have the iron nucleus interacting with this background radiation field here. The dominant part for this, because of the threshold nature of this, you can actually see that, the threshold nature of the cross-section here, where we want to interact with really the infrared background here. So we could convolve those two when we get this shape here for the energy loss length of the high-energy nuclei. Now, I have to do this in terms of doing a simulation of the propagation of ultra-energy cosmic rays. Then you have to do this sort of calculation for all the different species, and then work out a decay network, and it becomes quite numerically tedious and detailed. But this is the bones of it is this. Okay, and so then we got to put a distribution of sources for our simulation, so spatially that is. So we put these logarithmic shells of sources that I want to use to get across a key point. That is that if we look at the arriving energy flux of the cosmic rays as a function of energy, we can see that, like, for example, from this red shell here, this is the flux here is dominated by that shell, and then because of the interaction, or the higher energy the cosmic ray, the more photons it can interact with, it can achieve central mass energy sufficient with lower energy photons, so that the cosmic rays have to arrive from more and more local regions, and so we get to the point here where we essentially are probing pretty local regions with our ultra-high energy cosmic rays. Okay, and along with that, I'll show you this is the RMS that we get for such a calculation. Okay, and the reason I've gone through this is because I want to explain why we can use this actually again as a magnetic field probe. If the situation were like this, and the sources were actually homogeneously distributed, and we just turned a magnetic field on, actually not much would change. The more distant sources from the distant shells wouldn't be able to, their cosmic rays wouldn't be able to arrive, but that would be compensated by the more local sources. The trapping effect would mean that those local sources actually would become a bit brighter. So the arriving flux would stay the same. But there is a distance to the nearest source. Some of these inner shells certainly aren't filled with sources, and such that the magnetic field can have an effect. So this is what I want to show you here. And let's play a little game where we say, what if the sources are no nearer than 27 megaparsecs? And let's go to an extreme case of an iron-only type source. Okay, in terms of the spectrum, you can fit the data, and the magnetic field actually has a very marginal effect on the spectrum. Because we're in the regime of small angles, the deflection, and we're not really hitting very heavily diffusion, full spatial diffusion. However, that said, the effect on the RMS is much more significant, since the cosmic rays still arrive, but they arrive much lighter. So here I've shown you how the composition changes. So here's the no magnetic field case, and this is the 0.1 nanogauss, and this is 1 nanogauss. You can see that in terms of fitting the RMS data, we'd have a big problem if the fields were as strong as 1 nanogauss and the sources were more than 27 megaparsecs away. And I wanted to also remind you that this is a very extreme scenario. It would get much worse, for example, if the cosmic rays were lighter essentially because we would be starting off with lighter species, and so that the disintegration, they would turn over to protons more easily in terms of arriving composition.
Can I ask a very
Okay.
naive question?
Yeah.
The X here has a unit of grams per square centimeter, so that's a flux.
No, so grams per square centimeter, that's the grammage between the particles for the, so if my cosmic ray has to propagate, it comes through the atmosphere, and the amount of atmosphere it comes through is called the grammage, and it's measured in grams per square centimeter. For example, well, of course, I can't remember the number exactly right now. Perhaps someone in the audience. The grammage of the atmosphere is 1,000. Okay. It sounds too good to be true when it's a whole number, so I don't trust. Okay, but anyway, there's a grammage. Yeah, exactly. Okay, so anyway, that's what the magnetic field does. And there's one other factor that I wanted to remind you that I've not been optimistic in these calculations is that what about if I had a lower energy, maximum energy of my sources? I could have reduced the maximum energy from, in those calculations I was using 10 to the 21 eV, I could have reduced it to say 10 to the 20.5 eV or so. And the reason I can't do that is because then I would have problems measuring the actual, fitting the actual SED data. Essentially, the fact that the Auger detector has seen this data point out here means that the cutoff does sit pretty high up. Okay, so I've not been very optimistic. Okay, so that's part. That's the part of my talk where I wanted to talk about using cosmic rays as a probe of the extragalactic magnetic fields. And now I want to move over to using gamma rays. So first off, using a neutral particle, why would that work? That's because I'm using very high energy gamma rays that will also interact in these void regions and make high energy pairs. And those pairs will cool through inverse Compton scattering, and the secondaries will arrive to Earth coming from my blazar in this scenario here. And you'll see that I get similar interaction lengths to what I had for cosmic rays. It's not really a coincidence. The high energy photons here, they interact with the same target photons. These are the infrared background photons as my cosmic rays. And the cross sections, well, they're within a factor of 2, they're exactly the same. Okay, so again, like before for the cosmic rays, if you're going to understand how to do these calculations, you need to go through a little bit of the cascade physics of what's relevant. It's very simple. A cascade is just a repetition for an electromagnetic cascade, as the Cherenkov telescope people would know in the audience. Very simple cascades. You've got pair production and inverse Compton scattering repeating itself. And in terms of the cross-section for these two processes, they're also quite similar. If you look on this plot here, I've got cross-section as a function of center of mass energy. And if we go above the threshold for pair production, which is this is the pair production line here, the two cross-sections become very similar. And the splits, they're much less, let's say, symmetric. And the symmetry disappears down here. Essentially, inverse Compton has no cross-section and can continue to occur, whereas pair production, of course, dies off very quickly. Okay, so like before, if we want to understand, we're going to apply the theory of cascades to the observations of high energy blazars, we're going to need to understand these loss lengths here. Again, like before, I'm going to calculate these loss lengths as a function of energy. I need to convolve my cross-sections with my target photons. I've changed the representation, but this slide here is exactly as the one I showed you back for the cosmic ray slide before. The target photons is exactly the same. This is the CMB, and this is the infrared background. And it's actually sort of this part of the infrared background that we're really probing with these cosmic rays. Right. Sorry, not cosmic rays, with these photons. Right, so that's a lot of cascade physics I've just given you, but you don't really need all of that cascade physics. It's actually, what's really relevant is much simpler. If we start off with our 10 TeV photon coming from our blazar, it's going to interact, I've put here, of the order of 100 megaparsecs or so, to make our pairs. The pairs then cool very quickly. You can read off here, so if we're sitting at 10 TeV, and we made pairs within a rough 100 megaparsecs or so, and those pairs cool within, let's say, 0.1 megaparsec. Okay, so, and then the secondaries produced through the inverse Compton process will arrive, or will be produced with 200 GeV, okay? And this two-generation approximation is actually quite sufficient, essentially because we start off only with 10 TeV photons. The higher in energy that the blazars can output their photons, the more relevant the development of more complicated cascades is. Okay, so before I move on, I wanted to mention something that's relevant. So I know that Christoph Brummer is in the audience, and so I want to mention some work that he did that suggests that so I've been talking about inverse Compton cooling, and it's been suggested in this paper here that, that this can be outcompeted through plasma cooling effects. Okay? So in that case, that the cascade would be killed just by the effect of the plasma itself. Okay? So in his paper, he calculated some linear cooling times for this process, and it was much shorter than that for the inverse Compton cooling. I only want to address this briefly because the situation has become a little bit more confused. I'm sure we will talk about this afterwards. But anyway, in terms of, this was a linear calculation, there's some secondary physics to take into account. And this has been done by two separate groups, and they get vastly different results. So, unfortunately, the situation has not been really cleared up very much. It certainly looks like things become a lot more close, so that the cooling times of the plasma physics can either be quite comparable to that of inverse Compton or severely longer. Okay, but I wanted to continue assuming that inverse Compton cooling is the dominant channel for my high-energy electrons. Okay, so I'm going to apply it to two different blazars, this physics that I've shown you. You could do it to many of these, and we have applied this physics to different blazars, but I want to choose you the best two that you can check on the papers on the web, or afterwards you can come on to ask me what the other ones would look like. But these are the best two, and essentially the rest are something a little bit similar, but not as clean. Okay, so 1ESO22. Now, why do I say it's such a good blazar for this physics? Essentially because it's a really hard blazar. So in terms of its SED, is E squared dNdE, the energy flux arriving in photons, it's hard like this. And so it's a very good test of looking for a cascade signature. Another feature why it's so good is because it also has, the flux is measured up to very high energies. So it's, the high-energy photons are observed to come from it, and they don't, even though you do see a suppression feature here, that suppression feature can be completely accounted for from just EBL absorption effects, such that we can put an intrinsic spectrum, which is this dashed line here, which with a cutoff which is quite high. So these are for quite conservative cases of 5 TeV cutoff in both cases. In fact, that's essentially the lowest cutoff that we could afford to have, and the cutoff could go to much higher energies, in fact, and you'd still get quite similar results. What would happen is the high-energy flux would be absorbed by the EBL, and it would be reprocessed through the physics that I showed you before, this repetition of pair production and inverse Compton cooling, to give us this universal spectrum like this, which in terms of SED is flat. In fact, a flat SED for sources that are seen to emit really high-energy photons this flat SED should have been, or is expected. And the fact that it's not observed is surprising. And is what's led us to be able to calculate these limits on the extragalactic magnetic field. It doesn't mean that the extragalactic magnetic field is measured. It just means that if the extragalactic magnetic field were any weaker than that, then the flux that would arrive would violate these data points here. Okay. I should also reiterate that this has only been possible recently, since we've entered this exciting time in high-energy astrophysics of we can cover here, you can see 4 decades in energy, simultaneous observations of blazars, which has been possible. So this is Fermi data here, and this is Hess data here, this is Trenkov data. And so it's this, with this combined data sets that we can do this sorts of probes. Okay, so just to focus on how what the different spectra would be like if the magnetic fields were different. Here I've put some different lines. So 10 to the minus 17 and a 0.5 Gauss would be this line here. 10 to the minus 17 Gauss is around this line here. And this is 10 to the minus 16 Gauss. And in fact, in terms of the constraints, you can't really rule out this line here. This is a borderline case, but it's still acceptable within 3 sigma. And so, but you can exclude this line here. So 10 to the minus 17 Gauss is essentially where the limit sits. And that the field weaker than that would be a problem. Okay. And then you might ask me, is there anything special about 10 to the minus 17 Gauss? And the answer is not really. It's essentially because the Fermi satellite's been up in space for, well, I did this calculation, it had been 3 years, now it's a little bit longer. But it's because we've got simultaneous data for only 3 years. So if in terms of delays of I drew this triangle here, and of course the straight line path is like this, and the delayed path is like this. So in terms of the time delay that's incurred on going this longer path, you get delays which go with delta squared. And if I don't want to have delays longer than 3 years, longer than I've had these simultaneous data for, I'm not allowed to really go to stronger than 10 to the minus 17 Gauss field strength. So here we've got the 10 to the minus 17 Gauss line here. I've been using tens of GeV photons for my constraints. And you can see that if I want, say, 3 years, I can't go to stronger magnetic field strengths. I can't probe them with this method. So in terms of using the SED as a probe, or the SED of blazars as a probe of extragalactic magnetic fields, I hit a wall. Okay, but there are alternatives. We can use angular information as well as energy information. So here I've done a schematic diagram of this high energy photons emitting from my blazar, essentially in a pencil beam, and then making those pairs, and those pairs deflecting in extragalactic magnetic fields and inverse Compton cooling into a sort of a broad spray of particles with a dispersion angle of the order delta max, which is just this cooling time over the Lama period. And for stronger fields, so I'm talking about femtogauss fields, much stronger than I could get before using my SED data, for femtogauss fields, I get sort of coherent, I get Lama radii of the order of 10 megaparsecs. I've got, like I was mentioning before, got cooling times of the order of 0.1 megaparsec, so I can get deflections of the order of 0.3 degrees or so from this effect. And of course, we remember that the Trenkov telescopes have angular resolutions of the order of 0.1 degree, so you actually have the hope of looking for the angular spreading of a blazar because of the presence of extragalactic magnetic field. And of course, and I showed you in the previous slide, it's sensitive to much stronger fields because we're using high energy photons. We are not constrained by the time delays because the time delay shrinks as we go to higher energy photons. Okay, so here I've put the angular dispersion. This is a preliminary work that I've been doing with Hess collaboration. I've put the angular dispersion of the photons observed from PKS 2155 and have done some different strength magnetic fields since my 16 Gauss, 15 Gauss, and 14 Gauss. If the field's as weak as 10 to the minus 16 Gauss, there wouldn't be any problem explaining the angular dispersion of the photons. But if the field becomes too strong, then here's a problem. You expect the cascade component of the photons arriving from the blazar to be more spread out than that's observed. It's a little bit confusing to understand, but I want to remind you that in these calculations, the cascade component is quite a subdominant component at the energies I'm talking about, of the order of 300 GeV. So we're talking about a factor of nearly a tenth of the photons arriving, and that these mildly absorbed, EBL absorbed photons will be arriving essentially there's a point-like source. We've got a strong point-like source with a mildly broadened cascade component, and we're trying to look for that extra, the spillage from that extra component. In fact, if the magnetic field is too strong, of the order of 10 to the minus 14 Gauss, this constraint ceases to work anymore, since the broadening effect that I've just discussed, it broadens it too much, and then it's essentially impossible to see this effect. These Cherenkov telescopes aren't looking out to really large angles. They're only going out to several, well, you can see in this plot here, we're looking out to 0.2 degrees here, so 0.2 degrees, so degrees squared. So, this effect is limited in the range you can look for it, and it's strong as a probe at 10 to the minus 15 Gauss, and then it dies off for stronger magnetic fields. Okay, but coming back, like I said, full loop, I wanted to wrap up what we've learnt using these different probes. The key points are that we are able to probe extragalactic magnetic fields with these 10 to the minus 10 Gauss field strengths with ultrasonic cosmic rays. At the moment, we can use, well, we can, if the ultrasonic cosmic ray improves further and we actually start to see sources, then the situation becomes really exciting. And we can start to hope to really measure the extragalactic magnetic field strength. Or we can use, like I showed you, using the composition data, sort of more indirect probes of the extragalactic magnetic field. But again, it's of the order of 0.1 nanogauss or stronger. That said, then I've also discussed two methods using the SED, that's the energy information of the blazars. We can use that to probe the extragalactic magnetic fields and exclude weaker magnetic fields in 10 to the minus 17 Gauss. Or, using the angular information, we can exclude this small region here. The width of this region, by the way, is limited by how high in energy the photons from PKS 2155 for this particular probe are observed. If much high energy photons were observed, then the constraints could become much broader than that. But essentially, the maximum energy photons from that particular blazar limits that constraint. Okay, so these are the points that I've just gone through. That ultrasonic cosmic rays essentially can probe the strongest part of in the allowed range of extragalactic magnetic field strengths. That because we know the EBL quite well, and we've got simultaneous observations in GeV and TeV of our blazars, we can probe and exclude 10 to the minus 17 Gauss fields. That we can use the angular deflection information just to probe this middle range here for a small patch at least. And that in the next generation, this is a point I could talk about afterwards, that the next generation instruments, of course, will improve things even further, and so these probes will go deeper into the uncertainty range that I've talked about. Okay, thanks. Angular.
Angular response.
Yeah.
Can you look at it from the other way? Can you go to where you see these edge ends, 100 MeV or something like that, and look at your detection? You know, I'm worried about it gets so broad because you've got too big a magnetic field. You
Right.
can't see anything.
Yeah.
And the TV signal gets completely
Washed out.
as you said.
Yeah.
But can you use detection rate statistics, TV, given you've detected something in about 100 MeV, you can observationally get a probability function, you see this thing. Can you use that information to say something?
Well, you know, as the picture changes, the picture changes as you go to stronger magnetic fields. It's not as obvious as you might have thought. If I turn up the magnetic field strength, of course, the particles will start to isotropize. The electrons will start to emit isotropically. Actually, that's quite a different regime. Then you'd expect that the whole region around the blazar to start to glow isotropically in cooling electrons, which is called a pair halo. Okay, and you can look for those. And the work that I was addressing here, simultaneously, of course, you don't just look for one, you look for all of these signatures, and those are much searched for as well. The caveat with those is that, if you remember, a blazar gets it's so bright because of the Lorentz boosting of the in the forward direction. And my beam broadened cascades, they continue to be bright because the energy flux is moving in the forward direction. Whereas if the magnetic field is too strong and the electrons start to isotropically, then that component can come down. It's harder to see. So it's how things change as you increase the magnetic field is a little bit difficult.
That's the point I'm trying to say. You just don't see it. But if
Yeah.
there's sort of some threshold, you know, if there was zero magnetic field, you'd see things as point sources at TV.
Right. But then,
you saw things with that Ibra, and you see a one. If you had enough sensitivity with TV, you'd see 1 to 1. Because you've got very good point source sensitivity.
right.
But you don't have that great sort of brightness sensitivity, so you miss them if they're broadened out. So
If they're too broadened. I mean, there are people doing, for example, people using Fermi data. Fermi sees much full sky coverage, essentially. So it's able to. People have looked for much broader pair halos and beam broadened cascades from the blazars, and and even stacked those all together and seen. And well, I don't know if you remember, there was a paper a while ago where they thought they had seen something, but there was a Kusenko and Ando paper from a few years ago. It looked like they had seen some broadened emission, and then. Following on from that, it looks more likely now that what had happened was there was a misunderstanding of the point spread function of the instrument used. But people are using statistical methods to look for these on broad scales.
Have you or anybody else have investigated the possibility that you wouldn't have pervading pervasive rather than
Patches.
patches which basically are produced by star formation and by AGNs, etc. So that you have a lot of islands in an ocean of matter.
Right, yeah. And that picture might come about, for example, from these, at the beginning of the talk I talked about the structure formation and then outflows from these regions that could fill pockets of the void with field. Essentially, the answer is not really, because the probes that I'm talking about, or the motivation for the probes actually, that the idea that this SED would be seen to be flat everywhere, and it's not. Sorry, flat for different blazars that emitted high-energy photons, that universal behavior that's not observed. The explanation for that using the magnetic field requires that the magnetic fields have very large volume filling factors. So these are 50%, this is very large volume filling factors. And the small volume filling factors that other models would motivate wouldn't be sufficient to explain this, the suppression of the flux like this. So, of course, that scenario's possibility, but that scenario would have problems explaining this, unless, of course, at the moment we have a few blazars, and it could be that along those lines of sight, it just happens that the volume filling in that direction is large. But we've actually got 3 or 4 blazars now, and they're with high energy emission and with these hard spectra. So the situation becomes, it seems less likely.
This picture can be reconciled in our modified picture of what happens to these gamma rays as they propagate through the galactic space. If you do have most of the volume of the universe is affected not with electromagnetic fields, then the only other possibility where the energy that is being absorbed goes into heating the surrounding media through a plasma instabilities. And that picture is quite likely not at all ruled out by the current literature, because if you account for certain effects that people didn't properly account for, so basically, if you read these papers between the lines, there are some sort of conflicting statements. If you account for those, that picture is not at all problematic. So I think the picture from point of view is perfectly viable in this alternative picture. What happens is see the gamma rays as the energy that is basically used for the power production, then it's sort of dissipated with heating the galactic medium.
Well, can I be devil's advocate? I'm not going to talk about the player plasma, but I want to ask another question. Maybe someone was going to ask anyway. What if the signature I'm talking about isn't real? It was mentioned. Oh, that's a shame. Okay, that didn't come out. But some people have suggested perhaps the statistical strength of this signal that I've talked about is not strong enough. What if we don't know the EBL well enough, and that the EBL is quite a lot smaller than the, and I say a lot smaller, the level that we're at now, on a logarithmic plot, it's a tiny difference, and that's a large difference now. So these guys here, it is Arlen et al., from this paper here, they've looked into this, and they've gone to quite extreme scenarios. You can't see this plot here, which is a shame. And they suggested that for this extreme case, that a zero magnetic field case is still allowed. I would dispute this because essentially this EBL model came from nowhere, and it looks like it violates some of the galaxy count points. That there's a limit to the EBL point, to the EBL region that you're allowed here because of the galaxy counts, and this is EV optical. Yeah, so essentially I would dispute this idea, but I wanted to raise it because it's something that's been discussed. Although the other point I'd like to raise is not so relevant. Is the very contrived spectral energy distribution that they inject into their source. But the data is pretty poor at the moment. I mean, the strength of the magnetic field, 10 to minus 17 Gauss, is the 3 sigma level, and if the data improved, if we could probe to SEDs slightly higher, then we could. The strength of this bound, this 10 to minus 17 Gauss, is much more with much more conviction we could say it than we can at present. It's only at 3 sigma really. No, I know. I'm answering a different question. Yeah. Okay. Right, you mean to look for broadening on, this is the angular broadening? Sure. We split the data into 2 groups and do the same analysis, and no difference was observed. There was an exciting time when we were doing the analysis, and we thought that we had, well, one of the problems is to know what the PSF of the instrument is, okay? So for PKS 2155, what we did was we took, it's a flaring blazer, so we took when it flared and it didn't the regular state it's in, and we took the flaring state as to give us the PSF of and then the ground state to be able to be the broadened. And it's interesting, if we look at the angular distribution of the flared and non-flared, it looks like it distorts, but it's symmetric, unfortunately. It's not asymmetric. But that's not a statistically significant effect, unfortunately. I thought I was really excited when I saw that, but it's not. Essentially, it's not genuine. But just one more point. maybe I'm understanding why you're asking that, because perhaps the blazar's not quite pointing directly at you, and it's slightly off axis. And if you do the calculations, it's true that you actually do expect an asymmetry in the angular broadening effects that you'd expect. Unfortunately, yeah, we didn't see any evidence of that. Okay. Sure.
Of course, it's right to what we found is the effect, and I don't know if it's or not, but the effect is very interesting because it could destroy the whole idea. Maybe you could explain, people should understand what we're talking about. So I think it's just the pairs which you produce, they could create some plasma stabilities, and they will just simply degrade because interactive plasma stabilities in a state to produce the second generation quantum effect. So that is the effect. Now, of course, it's a very brave assumption to get so far from the source. If you go to 100 megaparsec, if you estimate what energy you would have introduced by the pairs there, that is amazingly small. Maybe you are right, maybe not. I cannot believe it. I can only say that there are values for you. Tips are coming from that. And there was actually one paper by Iñaki, and that also was a bit controversial by Stiglitz. It's amazing that these people are citing to each other in the accomplishment, but they have their fields of magnitude differences. I think it's
six orders of magnitude.
That is really very bad reputation for teachers. If you cannot
decide.
And they acknowledge each other. That is fine. Thank you for Heidelberg and for me. So that was very fine. But something, what you are right, you wrote about that, okay, it's interesting. Some people should be involved in calculate. So far, only is Judy, is Nihat, now the question is, I want to say yes, I mean, it's surprising you didn't think that, but we're going to that. I talked about that to Saddev, Roland Saddev, and the Bishop Markov. Saddev, probably number one in the forward of the instabilities, and their reaction was extremely negative. And I guess we are going to replicate on that. So, but it's not criticism, it's fine. What we find is effect, but we should not put in this way. I put in the more not so aggressive way. We found the effect, and that will not work. That is, I think, the wrong way, because it should be conformed to what I say. I believe that it will not conform, but let's assume this is my way. It doesn't mean that maybe it will be right. Nevertheless. So you should put in different ways, saying we found the effect. If effect works, then maybe the cascade will be not developed, and that is all. But when we are putting, saying we found the effect, that doesn't work, and that 90% of the world ignores what you say. Some people suddenly ignore because they think they should not spend much time to confirm that plus 2 is 4. It's based on time. But I think they are also wrong. Some time will come and to need independent confirmation from real experts in plasma physics, and then we'll see. So I think that in a way that it's a bit not very clear. It's clear for you. Some people think it's just cannot be true by definition, but probably so we need time to see. And I hope some plasma physicists will be involved to calculate and see. And not such a treatment like Nihat and Schlickheitz, I think maybe they were referencing each other, trying to say, acknowledge each other and stop on that. So that's my point.
I think that sounds like something you should also discuss with dinner a little more. Are there any more questions?
No, okay.
In many of your pictures, I saw
Oh,
going down by 1 order of magnitude. No.
Sorry, what? No?
No, this one is
Okay. Yeah. In the Fermi data. Yeah. Yeah.
Does this mean that all these points are based on one?
Oh yeah, exactly. It's a photon. I mean, it's true. It's a photon counter. I mean, a Fermi is a 1 square meter instrument.
One order of magnitude down and half
I think of these height. Okay, again, we're at low statistics. This is when the cutoff, and you're running out of statistics of events here. There's Poisson statistics. Yes. Yeah. Yeah, this is statistical, and it's just Poisson statistics. So you're exactly like you said. It's 1 or 2 photons in that bin.
I have in fact 2 questions. The one concerns the last laser show. You see with this angular distribution and
right.
10 minus 14, 15, 16.
Yeah.
Would there be any difference between 10 to the minus 16 and 0?
In terms of the angular spreading?
Yes.
No.
For 0, you would also get something very close to the blue line.
Right. So with the
setting an upper limit of something like 2 times 10 to the minus 16.
So with the PSF of Hess, as it is with this 0.1 degree resolution, it can only probe as this 10 to minus 15 up to a 3 times 10 to minus 15 Gauss range. And if it's 10 to minus 16 Gauss, minus 17 Gauss, or 0, the angular spreading would not be observable with Hess with its present angular resolution. But the SED information is what comes to play for smaller magnetic fields. You can probe the smaller magnetic field range because of the, like I discussed in the...
Well, the other question concerns when you calculate the propagation.
Right.
I understand you will have to assume something about the time dependence and about something like the distribution of the wavelengths, the variability of the...
Right.
You have to make some assumptions.
That's right, that's right. So for if I'm going to do a simultaneous SED, I'm not if the field was too strong, I haven't got the slide here. If the field were too strong, let's do this one. If the field were too strong, then the photons arriving here and the ones arriving down here. Yeah, so the energy, the photons arriving down here, if the field was stronger than 10 to the minus 17 Gauss, they'd be arriving more than 3 years after these guys here. Okay, so, and then you wouldn't be, you're not allowed to use this as a probe of the B fields for such a range because of the time limitation effect that you talked about. Essentially, 10 to the minus 17 Gauss field means that the difference in time for these photons and these photons is about 3 years. Yeah, to arrive.
I think with that, we kind of run out of
All right.